So I've been given the honor of introducing our keynote speaker today, Peter Cundall. And um, I could sit up here and go on about all of Peter's accolades, for which there are many, right? Being in the national academies, and having some citation classics, inventing numerical methods. He even has a Wikipedia page with his picture of his face disintegrating into particles. Look up DEM, distinct element or discrete element method. Um, and but more than those, I want to kind of relay personal anecdote about Peter. So he came to the university, University of Nevada, Reno, where I was a graduate student, and to come help us simulate earthquakes, foam quakes with PFC. And we got along pretty well. I didn't know Peter from a hole in the ground, and he didn't know us either at the time, right? This was 20 years ago now. And we got on well, and Peter came with us to a Southern California Earthquake Center meeting afterwards with some of the biggest seismologists in the world to talk about earthquake rupture simulations. Peter gets up and tells them what they're doing is all crap and that 3DET could do it 30 years ago. And he was not wrong. And, it's one of the things I admire about Peter is that he is very intellectually honest. He'll call a spade, but also the few times where I've seen him be wrong, he'll turn around and change his mind, right? He's very intellectually honest. And not only is he intellectually honest, he is excited about science, yeah? And he always has been. He's always been curious. And I really admire that as well. So he's going to, as you can see from his talk, he's going to talk to us a little bit about his excitement for running numerical simulations and learning about science, learning about the world. So, Peter, if you wouldn't mind.
Thanks, Matt.
We can.
Okay. This is supposed to be light entertainment, so it's sort of a relief from some of the heavy stuff. It's mainly because I'm retired and I have to find something to fill my time in. Nobody gives me any consulting anymore, so I might as well just look in Wikipedia and find something interesting. Anyway, here's the large scale. I'm going to give 3 examples: one large scale, medium scale, small scale, and this is the large scale. When you consider the moon orbiting the Earth, clearly everybody knows, it pulls tides backwards and forwards and does all this stuff. But it got me interested. Well, how much does the actual Earth move during that orbit of the Earth? How much does it move during one moon orbit? And I couldn't find anything anywhere, but probably somebody here knows it. So we could simulate it with PFC 3D by adding a fish function that supplies the gravitational force due to Newton's universal gravitational law. And here's all the constants, which you don't need to write down. So if you look in Wikipedia, the orbital velocity of the moon is just over 1,000 meters a second. So that corresponds to an orbital period of 27.2 days, which is a bit low because I'm only modeling the Earth-Moon system, whereas in fact the Earth moves around the sun, and so the moon executes a kind of spiral motion in space, and that lengthens the time of orbital period. If we're interested in just the periodical displacement of the Earth without drift through space, clearly the starting conditions have to be zero momentum. So that first equation has to be satisfied, which gives us the initial velocity of the Earth, just over 12 meters a second. So this is what the starting state looks like. Here is the Earth with that velocity. Here's the moon. And this guarantees that the system will become stable and won't migrate into space. So we do a time step of 80 seconds with PFC. And clearly, here is the motion, the Earth displacement as a fraction of its diameter. So clearly goes one way and then goes the other way and comes back to where it started. But it turns out this, as a fraction of the diameter, it's 37% of the diameter of the Earth. And I thought, holy buckets, that's incredible. I thought, it'll be a meter or something. But I don't know whether it's true or not, but that's what PFC gives. And well, everybody believes PFC. So I thought I might do a simple calculation. So, if you just assume that the Earth-Moon force is periodic, clearly, as the moon goes backwards and forwards, it causes a sinusoidal force on the Earth and can be expressed as this equation. So the acceleration is obviously given by the force over mass, and you can integrate it first using that initial condition we talked about, and then integrate again, and you get this equation. So if we step through time again by 80 seconds, get the same graph. So, it's exactly the same. So unless I was wrong twice, this to me is amazing. But somebody in the audience probably is some kind of cosmic scientist or something, so will point out where I've gone wrong. So anyway, that's the first example of a large scale. And then secondly, this is the intermediate scale. And here the wine comes into play. And this is, I don't know if you know this, but if you hold a bottle of wine and then sort of whack it on it has to be one with a cork, obviously. You're not going to blow a screw top off. But you can open a bottle of wine by banging it against a tree repeatedly. And that's interesting because I don't know if that same story you recounted, because I remember being in Menlo Park with all these big mucky muck scientists who know about fluid mechanics, and they hadn't bought a corkscrew. They had a little party, with wine out the back at Menlo Park. And I said, oh, I can open that. I started banging this, and there's these physicists, how does that work, Oh, well. I don't know if it was that occasion or another one. I think it was another occasion. So this should go, you even get the noise. And then
That's good.
That's my daughter. So we get 2 millimeters of cork comes out, and a few more bangs, and about half the cork has come out. Okay? And clearly, if we keep going, but at that point, actually, you can pull the cork out by yourself. But so, how does that work? So, what? What now? What's funny? What's funny? Why are they laughing? Oh, okay. So we model this with FLAC, an axisymmetric grid. And clearly, the grid is aligned in the y direction, but one problem with this is that the gravity you can't put gravity perpendicular to the axis of symmetry. So there's no gravity. So I'll tell you a trick later on of keeping the wine in contact with the cork, because what actually happens is that when you bang it against a tree, after one bang, the wine settles down and comes up to the cork again. So, how do you do that? I'll show you how. So here we have the cork, and it's pre-stressed, and here's the tree. Obviously, we don't have to model a lot of aspects of the tree. The reason it's a tree is that if you banged it against a brick wall, the bottle would break. So you have to have something with a bit of compliance. So this is a bit busy, but all the components are modeled as elastic. Typical properties of wine, cork, glass, and the tree modulus is little bit lower than that of glass. And it's done in dynamic mode, large terrain, with a low stiffness damping. And I pre-compress the cork to 1% strain because clearly, when the cork is put into the bottle, it's pre-stressed. And I gave it a friction angle of 30 degrees to the wine bottle. So I give it an initial downward velocity of 3 meters a second. I had to kind of guess that, but I looked on Wikipedia, and any idiot can throw a baseball between 20 and 30 meters a second, which is quite a lot. So I thought, well, let's be conservative. Let's have this person give it a 3 meters a second. So what happens after one strike? This is the relative displacement between the cork and the bottle top. And you can see it's moved quite a bit. And it probably corresponds to that first picture you saw of me in the backyard of my daughter. So we've got some kind of movement. Now I do 10 more cycles of that, but at 5 meters a second. And I should say, just to save computing time, I split each cycle into a dynamic and a static part. So that here's the dynamic part where I have low damping. And then after the things have moved a bit, I put it into static mode in order to get the equilibrium, and then do the next whack to an equilibrium. And this is the displacement between cork and bottle top for those 10 whacks. That was the original one I showed you previously. But the takeaway is the cork's already halfway out of the bottle. So, and here is the slight cheat. Is at the top of the wine column, I rezone the wine to be in contact with the cork just before the next whack. And this simulates the sort of recovery due to gravity that I can't model in an axisymmetric mode. So I think it's reasonable assumption anyway. But what's actually happening? Why? So let's consider a simpler thing, and this is a common kind of scenario in modeling. Is you have something that's quite complicated and you have no idea what's happening. So you make a simpler model of the model. So here we go. What I've done is just cut off the top. So I've just got a single column of wine and bottle. So just the lower part of the model. And I do one whack. But here you got this is the displacement of the top of the wine column. So obviously it goes down. I'm sending it with a velocity of 5 meters a second. Then when it hits the tree, it reverses. And it's just like, imagine you've got a deformable ball and you throw it against a wall. Well, what happens? Hits the wall, comes back. So it's just a rebound, in fact, from the wall. And it keeps on going. It'll keep on going like that. It's an elastic system. So that's a sort of simplified version of what's happening. But in reality, it's more complicated. Here's the initial velocity, but this is much faster, the rebound, because due to the constriction, the wine bottle amplifies the motion because the area reduces by a factor of 10. So it actually rebounds much faster than the simplified system, and does a few other things because you get this cork interacting, and it's a little bit more complicated. And it's interesting because this is the stress at the bottom of the wine column. This is the initial compressional impact, and it goes up, and there's a tensile area. That's about 1 megapascal. See, which is enough to probably cavitate the wine, which is interesting because when you look at that after that experiment in the backyard, you can see these bubbles. They dissipate after a while, but it clearly there's this cavitation that form bubbles. And I looked at the web and see, has anybody done this, on a YouTube, because everybody's done everything on YouTube. And there was an example, and some guy was all proud, of finding the mechanism. He says, oh yeah, there's all these bubbles in here, and they cause cavitation, and when they pop, they blow the cork out. It's actually the reverse. The bubbles are negative pressure, so they act to suck in the cork. So the bubbles are an effect, not a cause. So anyway, the flak model seems to reproduce that. Features of cork being driven out of the wine bottle. So it goes into compression. The wine goes into compression and then it rebounds. And when it rebounds, it drags the cork up a little bit. And it's irreversible because there's friction between the cork and the bottle. So repeated wax keeps on exiting it. So is anybody going to try that later on? Who knows? Because I'm not going to be responsible for any broken bottles of wine. I did in fact go on a sailing cruise on Lake Superior with bottles of wine, no corkscrew. So I whacked this against it has some sort of wooden things in the side of the boat, but actually we broke one bottle, but most of them we opened. So, there's something to bear in mind, Okay, now we come to the small size. So this has interested me for a long time. And again, there's probably gurus out there who know all about this. But where does friction come from? Because molecules are reversible. You've got a body composed of molecules, and they conserve energy. So where does friction come from? So if you imagine two blocks moving past one another, clearly all these are bonded, if you like, or stuck together with molecular forces, and the interface is not bonded, so that there are attractive forces, but they can be broken fairly easily. So what actually happens, in my view, is that this is like a bumpy road. You've got these sort of nobules going past each other, and this generates kinetic energy because the little particles are bobbling up and down. It's like a bumpy road that imparts kinetic energy to the molecules. But this is not like wave mechanics. It's not a coherent wave like a P wave or an S wave. This is incoherent, chaotic motion. So what actually happens is this energy of chaotic motion is radiated into the blocks. In other words, they get hotter because the definition of temperature in a solid is the kinetic energy of the particles. They're vibrating with a certain amplitude. And some in the literature, these are called phonons, but that's a sort of quantum mechanical concept. There's no quantum mechanics in this, by the way. I'd really like to understand quantum mechanics, but I've so far come up against ignorance. And anyway, so the blocks heat up. And the temperature is proportional to the mean kinetic energy. So this I postulate is the origin of frictional dissipation at an interface. So we model this with PSC 3D, with zero damping, actually exactly zero damping, and hope to get a frictional force out of it. So it's a bit involved, but typically this is a long shear box with constant velocity boundaries. These red things are bonded balls, and there's a layer of unbonded balls between the two. This is shown here. This is a picture of the contacts. And these are unbonded balls, and these are bonded balls. And at the top and the bottom, they're controlled. And in this experiment, the motion normal to the sliding direction is fixed at the outer boundaries. So imagine it's got a, sort of frictionless sliding interfaces at the boundary, and the normal force is kept constant by a servo mechanism. And these are the typical results. Here we get the forces on one of the blocks. Obviously, they're equal and opposite. The shear force is quite noisy. The elastic regime, this is actually as it builds up, and then they sort of start riding over this bumpy road, and this is dynamic frictional sliding. So it's kind of noisy, as you'd expect, because it's generating kinetic energy. This is a normal force, so this is quite a low shear force in comparison with the normal force. And then if we look at the energy components, elastic regime, obviously it builds up energy. And then this is the boundary work. This is what the work that we're putting into the shear box. And where's that kinetic energy coming from? Well, it's coming from internal energy. Those bonds are losing energy. So you've got this array of balls that are glued together, and some of the energy of that glue, internal energy, if you like, some call it potential energy, but I really hate that word. Some of that energy drops. So the internal energy actually drops, but the kinetic energy increases during so-called sliding. Note that these are exactly balanced. So the boundary work is exactly equal to, this plus this. So, but with PFC, we're not modeling molecules with like a Leonard-Jones potential. I'm not going that far. But I maintain that the same physics works even if you use small balls. These are like with 1 millimeter radius with elastic force displacement or at contacts. So I think, we are getting similar physics. Well, that's what I think is similar. So anyway, the PFC results show that you have chaotic motion at that sliding plane that radiates into the body, bounded blocks, and then they heat up. So that actually, if you look at the temperature of those blocks, it's increasing. And I had some scheme. Obviously, if they get hotter and hotter, the thing just, goes crazy. So I tried a scheme whereby I froze those motions periodically, and it still keeps going. You can, if you look at the overall motion, it's still the same. It doesn't matter whether you freeze it or not. You're just taking away that kinetic energy. That's to say, you're taking away the temperature. So they don't just rattle themselves to pieces. So Amundsen's formulated 3 laws, and one of them I'm going to study here. The force of kinetic friction is proportional to the applied load, and everybody knows this. When you in your physics lab you slide blocks down planes and all the rest of it. So we can see whether that's obeyed or not. But I changed the model a little bit, because if you remember, you get a change of geometry. The two halves of the shear box kind of hang over one another. So I used a doubly periodic model. So it's periodic back to front and periodic from side to side. So you don't need side boundary conditions, but you can still impose, shear motion on the blocks. I also tried to introduce roughness. So along the sliding so-called plane, that's to say unbonded balls, what I did was deleted 10% or 20% or 30% of the balls along that sliding plane. And this corresponds to a roughness because, and it was randomly, deleted so that, this would cause sort of much more bumpy road. And then I did tests at 5 normal force levels and 4 roughness profiles. Unfortunately, this is the result. So it's not exactly constant. This is the friction coefficient, the apparent friction coefficient, which according to Amundsen's should be constant. So it wasn't. So there's more work to be done, understood. This is the nature of research, I guess. So, but at least it shows the effects of roughness. So the actual friction coefficient increases with roughness. There is a lot of literature. If you look in the earthquake literature, there's lots of stuff. People like can't remember his name, but anyway, there's a lot of experiments that show that friction is not independent. It's not constant. It's actually can be dependent, and depending on stuff, you have these experiments where you start and stop kind of sliding and you get very great variations of friction coefficient temporarily. So I don't feel that bad about it at the moment, but I'm still, looking into it, why this is. So, normally people present something and they say, look, this is the answer. Well, I'm presenting something and saying, look, it doesn't work. Well, let's just look at it a bit more and see what happens. But in any case, what we have demonstrated is there's a mechanism for dissipation from an energy conserving interface. There's no energy dissipated at the interface. It's simply that that interface is rough and it radiates kinetic energy into the body and heats it up. And also we've demonstrated that there is a increase of friction with increasing roughness. So that's it. This is the examples I've given a spanner size effect of 10 orders of magnitude. So it's amazing that I guess PFC can do that sort of thing. But more importantly, it's fun. I think it was Yoni said it. Part of modeling is fun, and it really is fun, particularly for a retired person. It keeps me busy and stops me drinking too much. So that's it. Thank you. Yes, if there's any questions, I don't know what questions could possibly arise from that mishmash of.
Oh, Dave wants to.
Of course, I have.
Oh, of course, you have a question.
Okay, now model that last one where you were sliding the two surfaces. I assume you didn't use a micro friction coefficient, right? Of course not.
No, it's all frictionless.
Exactly.
No damping, nothing. There's no mechanism. There's no microscopic mechanism for dissipation of energy.
Exactly. So the only place energy can go is kinetic energy and
exactly, and it's
compression of the interfaces. Yeah. Okay.
Yeah. Yeah. In fact, I control the normal force, so that in fact, there's no energy dissipated even in the motion normal to the shear box. So anyway, there you go. Yes.
interest in the wine experiment. You know, the corks are oxidic materials. It means that when you compress them, they suck in.
Yeah, I know. I'd modeled that.
Did you model?
Yeah.
That might.
I put the proper Poisson's ratio in for cork.
Okay, so did you get that oxidic behavior in your model?
Yeah, but the thing was, they were pre-stressed because when they put the cork in, they don't want to pop out immediately, so they always pre-stress it. I guess they use weird materials now, don't they? It's not just cork; it's some kind of synthetic materials. But so I don't know how they behave. But yeah, it is kind of interesting. Yeah.
And so the wine itself is just a material with zero shear modulus? Is that
Correct, yeah. Yeah, so it's just bluffing around.
Yeah, okay.
But the problem is, as I said, I had to, in the horizontal version, after you give it a whack, it settles down and it comes up against the cork. So I wanted some, kind of synthetic way of bringing the wine back to the cork before the next whack. So that's why I did that rezoning, and it seems to work reasonably well. I've never done it with white wine, I must say. So I don't drink white wine, so I don't know what happened.
There's one more comment.
One more comment.
Yeah.
Here we can have a very good understanding of the particles at different scales. And my question is, what do you think about this new trend of moving towards black boxes, such as artificial intelligence mechanisms, where we don't see all the discussions that we just had, like here we have a normal force, these particles behave like that, the kinetic energy does that, the potential energy does that, the friction does that, but we don't have those outputs from these new trend that we are moving towards. So what is your opinion from moving from what we do, what we can see, towards something that we cannot see?
I know what you mean. And the best person would be to ask Jason about that. But I mean, I'm still a bit skeptical of the sort of machine learning scheme. I mean, to me, it's a big curve fitting scheme, but you do leave. It's just like AI. I mean, if you use ChatGPT and it gives you a whole little essay about something, you've got no idea how it did it. And the people who designed that have got no idea how it came up with that. So, with AI, you tend to lose a lot of understanding of how it came up with that conclusion. So I don't know. I guess it's still early days. In fact, Jason's going to talk about that this morning. Where is Jason?
Yeah, I would just give the comment that machine learning is just another tool to help understand these kinds of concepts. And I hope that Christian, Chris, and I can kind of show our work in machine learning that's just been another tool to help understand the mechanics of the things that we're working on. So I agree about the black box, and there's danger in that. So,
but how does it let you understand the mechanics?
That's one of the criticisms of machine learning, is the lack of explainability of why the model gives the answer that it does. But in specifically what the first two presentations are about are like easy to use tools that essentially allow you to very quickly change the inputs and see the outputs. And it's helped me be able to understand the system by manipulating its inputs and quickly seeing the outputs. So it's like giving you the answer a numerical model would give a little faster tool to use. So. But yeah, I mean, it's all underlying this physics. And then there's another take on it, which is a pure data thing. And Chris Thielson will talk a little bit about that. Thanks.
Okay.